sorry, there seems some network issue with me. So are you all able to connect now? So excuse me. So those who logged in, try to solve the previous class problem. Yeah, Banu Meena, are you there?
Yes, sir.
Yeah, could you please tell me the answer?
Sir, actually, I just joined this meeting, sir. I am previous earlier on that meeting, sir. So I didn't started, sir.
Okay, but did you note down the sum or no?
Yes, sir.
Okay.
You saw me, sir, previous class, no, sir?
Yeah, yeah, same
That session
class. It
only,
is
no?
correct, correct, correct. So we are continuing the
Yes,
same
sir.
thing.
Yes, sir. I'm doing that.
Okay, very good. Carry on. Dasar Jagadish,
Yes, sir. Sir.
could you able to calculate what is the mu1 and mu0 by interpolation method?
Sir, no, sir. Just now came into this meeting, sir. I am in previous meeting. I don't know what to say about that. I did not see
Uh,
that.
no, it was a problem with my network only. So there was some accidental drop in it.
Yeah. Okay, sir. I'll try.
Okay, कोशिश कर लो.
Sir, can you
Bhavyasri.
show the table, sir? So mu1 and mu2 table, sir.
Yeah, so these are the tables. So everybody. So I also repeat. So in fact, if you are not means acquainted with the speaking in English, you can speak either in Hindi or Telugu. So I can able to answer only Telugu in English. But I'm not much conversant with the Hindi, but I still could able to answer little bit. अगर आप पूछना चाहिए तो पूछ सकते हो. There is no issue. So and those who are hailing from Telugu region, so if you want to ask in Telugu, I don't have any absolutely no problem. Okay, so this is the reality of the sum. There are two different factors that one has to pick up from these two different tables. One factor mu1 is related to the function of df by b, while other function, that is mu0, which is a function of two geometrical parameters, That is the ratio of H by B and L by B. So in our case, we have considered the case 1 where the thickness of the soil air is 3.5 meter with a given UU, that is elastic modulus of the soil as 45 kilopascals. So from these two tables, you need to calculate the values of the mu1 and mu2. Q, that is intensity of the soil bearing pressure, given as 200 kilonewton per square meter. Width of the footing is 2 meter. EU is 45 kilopascals again, megapascals. So substitute everything into this equation after calculated mu0 and mu1. So then calculate the value of the immediate settlement. So it comes out to be approximately 5 millimeter, if not 5.49, because the values of the mu1 and mu2 are not exactly 0.65 or 0.95. You will get approximately this is 1.75 matlab, you will get approximately 0.660 or something, 0.60 or 0.55 जो भी है. So mu1 is 0.6 and mu0 is 0.6, mu1 is approximately 0.95 or lesser than that. So simply substitute into this equation, then calculate. What you get is elastic settlement in layer number 1. The thickness of that layer is 3.5 meter. 3.5 meter. Now, in a second case, so assume the total layer, the thickness of this total layer is 10 plus 3.5, so 13.5 meter. So 13.5 meter, and assume that the elastic moduli of the soil is 80 megapascals for the whole depth of 13.5 meter. So this is an hypothetical condition again. So in the first case, we have taken only the first layer with EU of 40 megapascals. In the second case, we have considered whole 13.5 meter depth, but assuming that EU of the soil is 80 megapascals. So having assumed this one, again recalculate H by B parameter and L by B parameter and DF by B. So here H is 13.5 meter, B is 2, so this comes out to be 6.75. Then L by B, that is remains same, so L by B is 4/2, so 6.5 means, so if you look at this table, this lies between 6 and 8. So corresponding to this 6 and 8, you need to pick up the values of mu0 or mu1 as 0.88 and 0.90. So pick up the value of mu0. In fact, this is a mu0, not mu0. Mu0. So corresponding to 6.75. Anyhow, this is either we can say only 0.88 and 0.9. So you can see approximately you can take it as 0.9 or lesser than that. So whatever. Then corresponding to DF by B, that is 1.5 divided by 2. So you will get approximately in the range of 1 to 0.9. 1 to 0.9. So just interpolate the value and take the exact value. Not necessarily you need to take the 0.95. While mu0 is 0.9. So now I have picked up mu0 and mu1 from these two different tables and substituted in this equation. Q is already known, 200 kilopascals. Width of the footing is 2 meter and elastic moduli of the soil is 80 megapascals. Substitute everything and calculate for the settlement, that you will obtain as approximately 4 millimeter. So in the first case, the elastic settlement is 5 millimeter over the layer thickness of 3.5 meter. In second case, there is an elastic settlement of 4 plus millimeter over a thickness of 13.5 meter. But here we made an assumption that the elastic moduli of 80 megapascals is valid for whole 13.5 meter, so which is not true, because corresponding to 3.5 meter thickness of the soil layer, the actual given elastic modulus is 45 meganewtons, 45 megapascals. So, but we assumed 80 megapascals. So, therefore, in a third step, I will assume only 3.5 meter, but assume EU of 80 megapascals, so that from the case summation of the case 1 and case 2, I can deduct the elastic settlement of the case 3. So this is the second step. I hope everybody has noted down. So then this is the third step. So in the third step, what I have done is I have again taken the thickness of the layer as 3.5 meter, but instead of EU as 45 megapascals, I have considered U as 80 megapascals. 80 megapascals. So for a 3.5 meter, there will not be any change in the values of the mu naught and mu 1, because this step is repetition from the step 1. So the calculation of mu naught and mu 1 is repetition of the step 1, which we have already done it. The only change is in step 1, the value of EU was 45 megapascals, but in step 3, the value of EU was 80 megapascals. So substitute all the numerals and calculate for the value of elastic settlement, that is SI third layer. So here approximately we will get more than 3 plus millimeter. Approximately 3 plus millimeter. Okay, so let me show the difference one more time so that there will not be any confusion. So this is the step 1, where we have considered the soil layer thickness as 3.5 meter and the elastic moduli of the soil as 45 megapascals. So substitute, we derived the values of the mu naught and mu 1 from these two given tables and substituted in the elastic settlement equation, and we have calculated the elastic settlement for the layer number 1 as 5 plus millimeter. In a second step, we made a small assumption. Herein, we considered the whole thickness layer as 10 plus 3.5, 10 plus 3.5, that is 13.5 meter. And we also made another assumption, that is the elastic moduli of the soil is 80 megapascals. 80 megapascals. So based on this assumption, again we have calculated mu naught for H by B and L by B, mu 1 for dF by B. So substitute into the elastic settlement equation SI2, and what we have calculated is 4 plus millimeter. But as we made assumption in the second step, that is considering EU of 80 megapascals for the depth of 3.5 meter. So in order to deduct that portion, we made one additional step, that is step number 3. So herein again, we considered the layer thickness as 3.5 meter, but whatever the assumption that we made in the step number 2 is compensated in the step number 3 by assuming EU of 80 megapascals. So there will not be any change in the values of mu naught and mu 1, which are very identical to that of step number 1. Only change is EU, that is instead of the 45, it will be now 80 megapascals. So substitute into this equation and get the values of elastic settlement layer number 1, layer number 2, and layer number 3. So once the elastic settlement for all the 3 independent layers has been calculated, so the summation is nothing but something like this. The total initial elastic settlement is 5.49 plus 4.28 minus 3.08.
Sir,
So yeah,
sir, we can't consider the thickness of the bottom layer as 10 meter directly. Means first we have to consider 13.5, then 3.5 and deduct that.
Correct. We can't able to consider the 10 meter directly. Okay. So here the SI3 is a negative because so we assumed in the step number 2 for a 3.5 meter thick clay layer or for 3.5 meter thick soil layer we assumed EU of 80 megapascals. So that assumption was deducted in the form of a SI3. So this is the total initial elastic settlement. So this is how one has to calculate the elastic settlement. Yeah.
Sir, what is the use of water table in this case?
There is nothing. So there is no consideration for water table effect in the elastic settlement. Its impact is only on the consolidation settlement, not on the initial settlement. Okay, so this is a simple and straightforward. And someone also suggesting some two important varieties of solving this one. One is by superimposing the load of 200 kilopascals instead of on top of the layer number 1 and distribute on top of the layer number 2. Yeah, you can also try it, so there is no harm. More or less you should get the same value of settlement, but there will be a mild distinction that you don't need to bother about. Yeah, so note down another sum. So the previous two sums were belong to the clayey soil, calculation of the elastic settlement in clayey soil. So this is on poisonless soil. A soil profile consists of deep, loose to medium dense sand, gamma dry as 16 kilonewton per cubic meter, gamma sat as 18 kilonewton per cubic meter. The groundwater level is at 4 meter depth. A 3.5 meter by 3.5 meter square footing rests at 3 meter depth. The total load acting at the foundation level, footing weight plus column load plus weight of the soil or footing is 2000 kilonewton. Estimate the elastic settlement of footing 6 years after the construction using influence factor method, that is Kamertman and Hartman. So end resistance values obtained from the static cone penetration test are given. So as a function of the depth. From 0 to 2 meter, the cone penetration resistance is 80,000 kilonewton per square meter. 2 to 4.75, 10,000 kilopascal. 4.75 to 6.5, 8,000 kilopascals. 6.5 to 12, 12,000, and 12 to 15 meter, 10,000 kilopascals.
Sir,
Yeah.
so in total gross load there is one term weight of soil or footing. What is that?
Weight of soil or footing.
Because sir, footing weight is already considered in first term.
See, normally when you construct any footing, what you initially do is you excavate the soil. Okay, then you construct the footing. Again, you refill the excavation because the footing will not totally occupy the whole excavated volume. Say for example, your footing depth is located at a depth of 1.5 meter, but your footing slab thickness is hardly 200 to 300 millimeter. Okay, so from the 1.5 meter, if you remove 0.3 meter, still a gap of 1.2 meter exists between top of the footing to the ground level. So this 1.2 meters is again filled with the soil. So that is what is the meaning of footing weight and the soil weight. So a soil profile consists of deep, loose to medium dense sand, whose gamma dry density is 16 kilonewton per cubic meter. Gamma sat is 18 kilonewton per cubic meter. The ground water level is at 4 meter depth. It is a square footing, size 3.5 meter by 3.5 meter. Depth of the footing is 3 meter. So the total gross load is 2000 kilonewton. So estimate the elastic settlement at a time of after 6 years. So which equation shall we use in this case? Could anybody throw small light on it? Which equation is valid for this sum? Which equation is valid for this sum?
So the equation which uses CPT in it.
CPT in it. Okay. Very good. Next. But in the CPT equation, there is no time factor to embed.
Sir, there is one creep correction factor equation.
Yeah, there is a one creep correction factor equation. So in this case, the method that's supposed to be used is strain influence factor method. That is influence factor method proposed by Smartman. So in the year 1978. The equation is something like S is equal to C1 multiplied by C2 multiplied by QB by IZ into delta Z by Q or something. I also did not remember exactly, but this is the form of the equation where C1 accounts for the depth of the footing, C2 accounts for the creep of or the creep effect, and IZ is strain influence factor, delta Z is thickness of the layer, Q is the intensity of the load, and there is also ES, the elastic moduli of the soil. Okay, let's see. Don't write this equation. So this is form of the equation. So here we have to use the strain influence factor method. So this is the graph that you need to remember, as I told in the exam as well. So this method is called as a strain influence factor method. So these are the predefined curves which are permanent. So there is no change in the values. Only thing is that first you need to pick up the valid curve from this one. So here in our case, it is a square footing. Square footing. So square footing means your L by B is 1. L by B is 1. So that means you need to pick up this strain influence line. So as per this diagram, this line starts at the foundation level with a value of 0.1 and increases and reaches a maximum value of 0.5, but at a depth of B by 2. At a depth of B by 2. And the strain influence factor becomes 0 at a depth of 2B. At a depth of 2B. So now here B is 3.5 meter. So the maximum peak occurs at a depth of B by 2 means 3.5 by 2. So B by 2 means 3.5 by 2. So this is 1.5 plus 1.75. So this is at a depth of 1.75 meter. So the strain influence factor at the foundation level is 0.1. At a depth of B by 2, that is 1.75 meter, is 0.5. And at a depth of 2B, that is 2 into 3.5, that is 7 meter. So at a depth of 7 meter is 0. So this is how one can able to construct the strain influence diagram. So for easy understanding, I'm redrawing this one. So this is the your strain influence diagram. So here the value is 0.1, and here at the peak the value is 0.5. Here the influence of the strain factor is 0, and here it is 0 meter. It is 0 meter per foundation level, 0 meter from foundation level, and at the depth where maximum value of the strain influence factor is happening, that is 1.75 meter. Just note down, this is the most important. Unless you could able to draw this one, you are not able to solve this problem. So the maximum strain influence factor of 0.5 is happening at a depth of 1.75 meter, and it further decreases and becomes 0 at a depth of 7 meter. At a depth of 7 meter. Okay. So whenever you are asked to calculate the settlement by strain influence factor method, your first step is to develop this kind of a diagram depending upon given type of the footing. So here it is given the square footing. So I have picked up L by B is equals to 1. So if it is not, then you have to pick up L by B of greater than or equal to 10. So in between, say for example, between 1 to 10, so either you have to interpolate, the best is only to interpolate the values. So construct both the diagrams and interpolate the values of strain influence factor. Okay, but now if you look at the equation, one of the particular term that included in the equation is the elastic modulus of the soil. So that elastic modulus of the soil can be calculated based on the cone penetration values. So therefore, ES can be taken as approximately 2 times of QC, where QC is cone penetration resistance. So the QC has been given as a function of the depth up to 15 meter. But what we require
Sir,
is up
in formula you have given 2.5.
2.5.
Yes, sir. For
Okay, no
circular
problem.
and square formula.
No problem. Actually, there are a lot of empirical formulas are there. You can consider anything, doesn't matter. Okay, either you can take 2 or 2.5. I hope it is clear to everyone how to construct this strain influence diagram. If it is not clear, please ask me. Because if you don't understand how to construct this diagram, then you cannot able to solve this problem. So I repeat again, the crux of this is picking up the exact curve between these two, which is corresponding to L by B of 1, which is nothing but square foundation or the square footing, and corresponding to L by B greater than or equal to 10, so which represents the strip footing. So since in our case it is a square footing, so where L is 3.5 meter, B is 3.5 meter, L by B is 1, so we need to pick up a predefined strain influence factor curve of which starts at the foundation level with value of 0.1. So this is called as a strain influence diagram. So what I would have done is, so I have considered the foundation level as 0 meter, and corresponding to which, based on this diagram, the strain influence factor value is picked up as 0.1. However, it has further increased and reached a maximum value of 0.5 at a depth of B by 2, which is nothing but 3.5 by 2, that is 1.75 meter. And from the peak, it continually decreased and reached 0 at a depth of 2 times of B, which is nothing but 7 meter. So this is how very simply you can able to construct the strain influence diagram. Okay. So now once this strain influence diagram is over, the next step is try to calculate the elastic modulus values based on the empirical formula. So here in this case, ES is approximately taken as 2 times of QC. Suppose if you see another equation, you can also consider 2.5 QC or 3 QC, but approximately between 2 to 3 value, 2 to 3 times of QC. Okay. So let me go to the next slide. So this is the complete picture of construction of the strain influence diagram. So as you can see, the strain influence diagram corresponding to L by B of 1 has been picked up. So it starts at the foundation level as 0.1 and increases to 0.5 at a depth of B by 2, that is 1.75 meter, and reaches to 0 at a depth of 7 meter. Now, having understood or having constructed the strain influence diagram, your next step is to divide the entire 7 meter depth into different number of layers. So the division also your discretion, depending upon the number of layers that you want to consider. You can consider any number of layers. Okay, so there is no particular rule that I have to divide everything into this many number of layers only. But here in this case, it has been divided into 4 number of layers: layer 1, layer 2, layer 3, layer 4, considering the easiness in the values of the bearing cone resistance. Considering easiness in the values of the cone resistance. As you can see, the cone resistance value varies, suppose say at 4.75 meter, which is corresponding to 1.75 meter in our case. So that means from the foundation of the foundation level up to a depth of 1.75 meter, there was no variation in the QC. So the value of which is 10,000 kilopascals. So therefore I have considered this whole thing as a layer 1. Layer 1, that is designated as delta Z1. Now thereafter, so from the 4.75 meter and up to 6.5 meter, there was variation in the value of the QC, which was decreased from 10,000 kilopascals to 8,000 kilopascals. So therefore I have considered between 4.75 to 6.5 meter as layer number 2. And again, from the depth of the 6.5 meter up to 12 meter, the value of QC is recorded as 12,000 kilopascals. But my strain influence diagram is terminated at a depth of 7 meter only. So meaning thereby, so from a depth of 6.5 to 10 meter from the ground surface, the value of QCs remains same, that is 10,000. But it is becoming the too thick, so therefore I have equally divided this layer into layer number 3 and layer number 4. So this is based on the easiness. If you wish, you can also consider, for example, you can subdivide layer 1 into layer 1 and layer 2, layer 2 into again layer 3 and layer 4, layer 3 into 5 and 6, and layer 4 into 7 and 8. You can divide the same thing into 8 number of layers or 4 number of layers.
So why layer 3 and layer 4 is divided?
Just to suppose if I take 6.5 to 10 meter, that 3.5 meter is becoming the too thick. So just to increase the accuracy, I have taken one additional value. That's it.
Then layer 2, layer 1 can also be done like that.
Yeah. That's what I'm saying. You can also subdivide layer 1 into another 2 more layers or 3 more layers, and layer 2 also into another 2 more layers or 3 more layers. There is no problem, absolutely. You are most welcome to do so. Okay.
Sir,
So,
can you explain it from the beginning, sir?
Okay. So your first step is to construct the strain influence diagram, considering the foundation level as the 0 level. So this as 0 level for constructing the strain influence diagram only. So based on the previous slide, we have picked up a strain influence diagram of L by B is equals to 1, because this is a square footing. L by B is equals to 1. For L by B is equals to 1, the strain influence diagram varies such that it starts with 0.1 at the foundation level and increases and reaches a maximum value of 0.5 at a depth of B by 2, that is 1.75 meter. From the peak value, the strain influence decreases continually and reaches to 0. So reaches to 0 at a depth of 2 times of B. At a depth of 2 times of B, that is 7 meter. That is 7 meter. So this completes the step 1, that is the construction of the strain influence diagram. Next, you superimpose if the cone penetration value has been given, cone penetration, or if elastic modulus of the soil has been given, elastic modulus of the soil. Now, if I look at my profile of QC, that is cone penetration resistance. So up to a depth of 2 meter, it is 8,000 kilopascals, and from the ground surface. From 2 to 4.75, it is 10,000, and 4.75 to 6.5, 8,000, and 6.5 to 12,000, and below 12, it is 10,000. So try to superimpose the same measurements on the strain influence diagram. So incidentally, my 1.75 meter and 4.75 matches perfectly. So therefore, I have considered from foundation level to 1.75 meter as layer number 1, wherein there was no variation in the value of QC. Second, the QC from 4.75 to 6.5 from the ground surface remains unchanged. So therefore, I have considered 4.75 to 6.75 as layer number 2. And from 6.5 to 10 meter, there was no change in the QC. So therefore, I can consider this as a single layer, that is layer number 3. But it is becoming the too much. So therefore, I have further divided this into 2 number of layers, layer number 3 and layer number 4. Okay, so this is how I have done it. So I have indicated layer 1 as delta Z1, layer 2 as delta Z2, and layer 3 as delta Z3, layer 4 as delta Z4. So my thickness of delta Z1 is 1.75 meter. Thickness of delta Z1 is 1.75 meter. So thickness of delta Z2 is how much? Anybody can able to tell me? What is delta Z2? It is 6.5 minus 4.75.
1.75.
1.75. Very good. 1.75. What about delta Z3?
1.5.
1.5. Okay. And Z4 is also 1.5, I guess. Because this is 6.5 minus.
No, sir, it will be
No, sir,
1.75.
1.75, sir.
1.15, 1.75.
1.75, sir, both are.
Achha, 1.75 and 1.75. Very good. So all layers are almost same. 1.75, 1.75, 1.75. Okay. So this is how you need to divide the entire thing into so many number of layers. Again, I will repeat. There is no particular rule that you have to divide only in this fashion. I have divided this layer based on the ease of the QC value. You are most welcome to subdivide layer 1 into 2 more layers, layer 2 into 2 more layers, or even more, layer 3 into 2 or more number of layers, layer 4 also 2 or more number of layers. Okay. So once
If
this is
the means if we take more smaller width, the accuracy will be more.
correct.
Okay.
If you consider more number of layers, your accuracy improves. That's it.
So sir means equal width we have to take like in this question. All
No,
are
not
1.75 only.
not necessary. Not necessary. You can take unequal depth also. No problem. Okay. Here if you look at, it looks like it is equal because the first layer ends at the peak of the iz, so that I can easily pick up the value of iz. That is only the convenience. Next step is, this is the equation for calculating the elastic settlement. SA is equals to C1 into C2 into Q multiply summation of iz into delta z by elastic modulus. So C1 is accounts for the depth of the net, the correction factor for the footing depth. So this can be written as C1 is equal to 1 minus 0.5 into sigma naught dash by Q net. Sigma naught dash by Q net. So sigma naught dash means effective overburden pressure at foundation level. So calculate sigma naught dash at foundation level, and C2 accounts for creep. That is C2 is equal to 1 plus 0.2 into log T by 0.1. Here time shall be taken in terms of the years. So time is given as I think 6 years. So 6 years. So substitute 6 in this equation and calculate the C2. Another value, that is Q net. So this is supposed to be calculated because in our case gross pressure of 2000 kilonewton has been given. Q net can be calculated as load upon area. But we need Q net, meaning thereby from the gross load you need to deduct the weight of the soil which is excavated. So this is the weight of the soil which is excavated. So 2000 divided by size of the footing is 3.5 by 3.5 minus 3 meter is depth of the foundation level and 16 is the dye density of the sand. So this is something nothing but overburden pressure. So 2000 divided by 3.5 minus 3 into 16. So what we will get Q net as 115.26 kilopascals. 115.26 kilopascals. Sigma naught is effective overburden pressure at foundation level, which is nothing but 3 into 16 only. Your sigma naught is 3 into 16 only. So as per this statement. I think I will stop it here only because so this is one of the important sum. I don't want to miss you people understanding. Like this slide is the most important. Unless you understand this one, then you can't able to understand the other things. In the Wednesday's class, I can able to discuss about all these things.